Okay, so here we are at the top of 182, lesson number 24. In this lesson, we see how we can use part of the quadratic formula to determine the nature of the roots of a quadratic equation, and we discover a brand new set of numbers called the complex numbers. Here's our demo. In our last lesson, we examined this graph. I called it graph D. I actually think we skipped that, that page, but anyway, there's the equation, y equals x squared minus 4x plus 5. Graph is here. And there are no x-intercepts, right? But we know that when we use the quadratic formula, we are finding x-intercepts. This was a discovery we made last time. To find the x-intercepts in general, you change the y to a 0. Yes, that's how we always find x-intercepts. And the quadratic formula is a perfect tool for solving equations that look like that. And so it's kind of strange because there are no x-intercepts, but the quadratic formula doesn't say, hey, you don't get to use me. So we're going to get some kind of answer when we do the quadratic formula, but there are no x-intercepts to get. So let's follow this process and see what happens. Remember, so I've got the parts there. See if you can just, from your memory, fill in the A's, B's, and C's. No numbers yet. Can you guys fill in A's and B's and C's? Raise your hand if you got it perfect. It's like a bunch, not everybody, but that's okay. Like I said, I won't require you to memorize that. I will provide that on any test or quest in which you need it. So let's start filling in the numbers here. Equals negative b. How much is the opposite of b? So actually, I'll do this. How much is b? Negative 4. So there's negative b, yeah, plus or minus square root of b squared. Again, b is negative 4, minus 4 times a times c. How much is a? 1. How much is c? 5. All divided by 2 times a. A is 1. Okay, so we'll just crunch the numbers here. Negative negative 4 becomes 4, plus or minus square root of negative 4 squared. Is that 16 or is that negative 16? 16, positive. Okay, is this going to end up being a plus or a minus after the 16? It's minus, just the single subtract sign. Minus 4 times 1 times 5, that's 20. Still divided by 2. And so we get 4 plus or minus the square root of, oh, that's a minus. Oh. Negative 4 divided by 2. And based only on the stuff we've seen in this class, that square root of a negative 4 is a problem. Yeah? Yes. Because we know that if you multiply a real number times itself, if you square a real number, you're going to get something positive all the time. It feels like maybe the square root of negative 4 could be negative 2, but it isn't, because negative 2 times itself turns back into positive 4, not the negative 4 we want. So up until this point in our class, we would be stuck. We would answer not a real number, and we'd be done with this problem. But now we're going to do further. We're going to go further with this one. What do we do with that square root of negative 4? We know from our earlier work with simplifying square roots that the square root of a negative number is not a real number. Can we give meaning to the square root of a negative number? And the answer is yes. Mathematicians have created a number system called the complex number system, and these complex numbers allow us to work with the square root of a negative number. Complex numbers are used in many fields, such as engineering, to find quantities involved in electricity, and in medicine to calculate the flow of blood in the bloodstream. Before we discuss the square root of negative 4, we're going to start with the square root of negative 1. Just a tiny bit of history here. The question of how to define the square root of negative 1 arose when 16th century Italian mathematicians tried to solve cubic equations. We're not going to talk about cubic equations, but here's an example. X cubed minus 15x equals 4. What makes this cubic and not quadratic? The x cubed, right? Everything we've been doing the last couple of classes involves an x squared. This is just the next order of difficulty. And in trying to solve these equations, they ended up inventing a new class of numbers, beginning with this definition right here. We denote the positive square root of negative 1 with the letter I. That is, we let I equal the square root of negative 1. Maybe put a star around that or circle it or something. That is our definition of a brand new class of numbers. If you see the square root of negative 1, you get to change it to an I. Square root of negative 1 Might be frightening to look at. It is not a real number, but it is a number, and we're just going to give a letter to it. And it's not so uncommon to give a letter to a famous number. For example, pi is approximately 3.14, but it's a number, right? And we just call it a letter for convenience sake. Same idea. Square root of -1, perfectly legitimate number. We're just going to denote it with the letter I for convenience sake. So once we have that definition, we can then do stuff. So we'll do these examples, but we'll just write them out here. So don't look at that. Square root of -4 equals. So -4 is really -1 times 4, yes? And we know that radicals work really nicely around multiplication. So we've seen this property many times now. And the square root of -1 is our main definition. What letter are we using for that? I, and the square root of 4 happens to be a nice number. That's 2. And so I times 2 is our answer. If it ends up being like an integer, then we typically put the integer in the front and the I in the back. So 2I. Let's try a different example. In fact, why don't we just make one up that isn't here? How about we try this? Square root of -18. Can you guys try this one with me in that blank space? Square root of -18. First thing we're going to do is rewrite it as what times what? -1 times 18. We're just going to do that every time we see a negative symbol. And then we get to split into 2 radicals multiplied together. First one has just -1. Second one has 18. This -1 inside the square root changes to what letter? I. It's just the definition. Square root of 18. So oftentimes you'd just be done. It would just stay square root of 18 with an I, but we can go farther with square root of 18 by further refactoring it as 9 times 2. Right, so now it's old because square root of 18 is one we've done many times. So this is equal to I times square root of 9 comes out as 3. Square root of 2 stays as is. This is a full credit answer, but I'll just again tell you the convention is if you have a nice number right next to an I, you typically put the number first and the I second. So I would probably change this to 3I square root of 2. It's also fine to write 3 square root of 2 and then put the I at the end. It's okay, it's all multiplication, but I would never do this. What's the danger in doing this? Yeah, like if you're just a little bit careless with your square root symbol, all of a sudden the I is inside, and that is not right. So that's why we put the stuff that is definitely not inside, we put it in the front, so we don't have this possible confusion. Okay, so I think that's good. So here's our more general definition. If you have a negative number inside, it just becomes an I on the outside, and then the number becomes positive. That's just the shortcut thing that we just did. If you have a number of the form a plus bi, then it is called a complex number. If it happens that b is 0, then this term right here just vanishes, and you just get real numbers. So that means that the real numbers are automatically complex numbers. So we have our friends, the real numbers that we've got many, many years of experience with. That is just a small set inside of this larger set of complex numbers. So all we're doing is expanding. We're not excluding the real numbers. We're not going to like a completely different world. We're just expanding our view of the world of numbers. So that means we can now finish this problem that we started up here. 4 plus or minus square root of -4 over 2. That's this first thing that's copied here. And now we can take that -4, and remember it just becomes an I and then a +4. So that's there, right? Square root of -4 becomes I, square root of +4. And it happens that square root of 4 is nice, so that just becomes 2 with the I at the end. And then stuff that you've got lots of practice with now, splitting into 2 fractions and simplifying. So 2 plus or minus I is our answer to that one. Okay. Again, quadratic formula finds for you x-intercepts. Looking at the graph at the top of this page, what were the x-intercepts? There aren't any. And so this is how that appears, is that when you find the quote-unquote x-intercepts, you'll end up leaving the set of real numbers and you'll have to end up going to these complex numbers, things with i's in them. Okay, next page. Is there a way to figure out how many solutions and what kinds of solutions a quadratic equation has without going through the entire quadratic formula calculation? Below each graph, you'll see the nature of the solutions of each quadratic equation, i.e. for finding x-intercepts of a parabola. So let's take a look at these few pictures here. I'm just going to put some dots on the x-intercepts. If you had to guess, what would you say are the coordinates of those two? Right, -6 and 1, 0 for both of them. Okay, vocabulary phrase from your past. A rational number is something that can be written as a ratio of two integers. For example, a half or -17/4. Anything that you can write as a ratio of two integers is called rational. The word ratio is right there in the beginning of the word rational. But if you can't write something as a ratio of two integers, it is called irrational. Common examples include all the radicals that aren't just perfect squares. So square root of 10 is an irrational number. So is square root of 11, square root of 12, square root of 13, square root of 14, square root of 15. But when we get to the square root of 16, what is that really? 4. And so square root of 16 is a perfectly nice rational number. But if it's not something perfectly nice, like 16, inside of a square root, it is irrational. So what that means over here is that these two numbers, -6 and 1, are they rational or irrational? Irrational. So in this case, we had two rational solutions, two rational x-intercepts. Looking at this next one, what's your guess for that number? Yeah, there's just a single one, and it looks like it's happening at 2. Is that rational or irrational? Rational. So in this case, we had just a single, just one rational solution, one rational x-intercept. Okay, then things get a little bit messy here in graph C. This was one that we looked at last class. And I think the number was something like -3.49, and then it went on forever. Do you guys remember seeing this on your calculator? And then this guy over here was 1.449, and that went on forever. And the way that we got those numbers was to type in some quadratic formula looking thing on the calculator. And a big piece of that quadratic formula is the square root. And I don't remember what the numbers were in this case, but ultimately you typed a square root of something on your calculator to get this. And if you type in a square root of almost any number in the world, is it rational or irrational? Irrational, right? Square root of 10 is irrational, square root of 11, almost any square root you can think of is irrational. And so we have two answers here, but for the first time they are irrational numbers. And then finally, part D, that's really the weird one. How many x-intercepts? None. But we can still use the quadratic formula. And in fact, we did. And we got what kinds of answers? We got the complex answers, the things with the i's at the bottom of the previous page. And how many answers were there? It looks like just one, but remember there's shorthand in there, plus or minus. So there's actually two. So the answer in this case is two complex, we might call them imaginary solutions. That's why we use the letter I for imaginary. Okay, so we've got this relationship between the pictures and the kinds of solutions you might get. All the stuff that I just underlined in blue is what we're going to call the nature of the solutions. It's how many do you have, and are they rational or irrational or complex? Those two characteristics are what we call the nature of the solutions. And so here's a definition, number 8. For the quadratic equation, ax squared plus bx plus c equals 0, the discriminant, brand new word, is b squared minus 4ac. Where have we seen that quantity before? It's inside the radical in the quadratic formula. Yeah? Negative b plus or minus square root of b squared minus 4ac, all divided by 2a. Okay, so let's calculate some discriminants here. Graphs A, B, C, and D came from these equations. They were all y equals, but I've changed them to 0 equals. And we're going to calculate b squared minus 4ac. Let's divvy up the work here a little bit. This first table, you guys are doing A. Up here in the front, you're doing B. You guys are doing C. Can you guys just calculate the discriminant for A, B, and C? And then share the answers with us when you're done. Okay, so go ahead and grab the answers from the other tables. Once you know how to do one calculation, you know how to do them all. So the answers were 49, 0, 24, and -4. And it turns out that there are certain characteristics of those four numbers that determine completely the things that we underlined up above in blue. Up in blue, we had 2 rational solutions, 1 rational solution, 2 irrational solutions, and 2 complex solutions. And I'm telling you that there's a way to look at those numbers, the 49, 0, the 24, and the -4, and know exactly what the answers are going to be in blue. So here's how. Let's start with the negative. That -4, remember, this b squared minus 4ac lives in the quadratic formula underneath what? Underneath what? Underneath the radical, right? So you're imagining a square root on top of each of these numbers. So the square root of -4 is what kind of a number? It's an imaginary. The square root of negative is where we get our i's coming in, right? Nick? If it is negative, so what's the next one you're looking at? Okay, so let's take a look at the 0. 0 is a special one. Again, remember that each of these numbers lives underneath a square root in the quadratic formula, yeah? So that 0 lives under the square root symbol. What is the square root of 0? It is 0. Now in the quadratic formula, you got a plus or minus square root of 0, right? Now whether you do the plus 0 or the minus 0, you're going to get exactly the same thing, yes?
Yes, because 0 is...
Right. It's the only number that you could add and subtract and not change anything, right? And so that means that normally the quadratic formula, which gives us 2 answers because of the plus and the minus, actually compresses to just a single answer in this case, right? Because adding 0 and subtracting 0 just gives you the same whatever answer. So if you get 0, then there's only going to be 1, not 2. Every other choice here is going to have 2, but there's only 1 answer. And in fact, that 1 answer, if you think about the quadratic formula, if I just decide I've got a 0 inside of that square root, then I can ignore the square root of 0 because that's 0, and then plussing and minusing I can ignore 2 because that doesn't change anything. And so the answer is just negative b over 2a, whatever that calculation gives you. But that right there is automatically a fraction, right? With no square roots in it. So is that going to be rational or irrational? It's going to be rational, right? The messy part is the square root, and it disappeared. And so not only do we know there's 1 solution, but we know it's automatically going to be rational. And in fact, if you look at part B, what was our guess for the x-intercept, the coordinate?
2, 0.
Was 2, right? 2 is a perfectly good rational number. It would never be the square root of 10 sitting there as the x-intercept. It has to be something rational. Okay, so we've dealt with what it looks like when the discriminant is negative. We've dealt with what it looks like when the discriminant is 0. The only other possibility is positive answers. But we've got 2 kinds, 49 and 24. Again, imagining both of these living underneath the square root, which one of them is friendlier? Is that 49? Because the square root of 49 is a perfectly nice number. It's just 7. And so our answer, our conclusion for here, if it's what kind of a number? If it's a perfect square. Then we have 2 solutions. Are they going to be nice or not nice? Very nice, because that square root of 49 simplifies to just plain old 7. And so nice for us means rational. And then our last conclusion, that number 24 is a positive number, but not a perfect square. And again, imagining that 24 under a square root, is the square root of 24 rational or irrational? Irrational. So we're going to get 2 answers, plus or minus. And in this case, they are both irrational numbers. And if we again take a look at graph C, our guesses for the, not our guesses, but what we saw in the calculator last class was something like negative 3.449, and then it went on forever. It is not possible to have one irrational number like the negative 3.449 forever, and then one rational number like 7. You can't have one of each. It's either both rational or both irrational. So it turns out there's a lot of structure here that maybe wasn't apparent when we first started doing the quadratic formula. All right, on the next page, so our conclusions all written out nicely for you. As you make your cheat sheet, you might include word for word what's written up there. If the discriminant is 0, one rational solution. If it's negative, 2 complex or imaginary solutions. If it's positive, then you need to ask one more question, and that's about whether it's a perfect square or not. If it's a perfect square, 2 rationals. If it's not a perfect square, 2 irrationals. Okay. So let's practice with the new discriminant and the old quadratic formula. Go to the activity on the next page, and let's see how far we can get.